Okay, so last week we talked about um, the eye, and so today it seems natural to talk about where the signal for the eye goes to, from the eye goes to. And so we'll talk about a structure called the primary visual cortex. Now you see this little wiggle, this little red line here. This little red line is the marks the edges or the shape of the valley called the calcarine sulcus. So anything that's a sulcus means it's a valley into the cortex, and you can see here that you get activity in around this place when you have this thing flashing in the visual field. But it only lights up when it's on the opposite side. So this is the right side, and when things on the left appear, then you get activity on this side. The other thing to notice is that when it's below where you're looking, then this the activity appears above this line, and vice versa. When you're looking above, it appears below this line, the calcarine sulcus. Okay, how does it do it? Well, here you have a picture of your eyes and the path to the visual cortex. And the thing to notice is that the green line here is always gets activated by a signal from the opposite side. So it goes through the eyes and hits the opposite side. And in case of the green one, the green signal is the signal from coming from the medial side of the eye, that is the side closest to the nose. That's the medial side of the eye. And then this signal goes to the opposite cortex along this green line, whereas a signal coming from the lateral side doesn't cross and ends up on the same side of the cortex. Now, where does a ganglion cell first project to? Well, there's two types of ganglion cells. One's close to the fovea we saw that had high acuity and could be useful in reading. And these guys project to what are called the parvocellular or small cells, small ganglion cells. And they go primarily to the thalamus, and the part of the thalamus they go to is called the lateral geniculate nucleus, or LGN for short. The stuff from your periphery goes to the LGN, but it also goes to the superior colliculus. Now, the superior colliculus is useful in the visual grasp reflex. That is, if, for example, one of you were to raise your hands, I would see the hand in the periphery of my eye and then do a visual grasp reflex to point the fovea at whatever person has their hands raised, so I can recognize who that is. So the signal from the peripheral retina doesn't have much detail to it, so you can't use it for recognizing what the object is. But the signal from The fovea goes to a different part of the LGN, and it has also high detail like the fovea does. So the other thing to notice is that the two eyes the signal from the two eyes stay separate. So the right eye, indicated in red here, goes to these red-colored layers of the LGN, and the blue ones, the ones from the opposite eye, go to these layers of the LGN. Now you notice that four of them are small-celled ones, so they're the ones coming from the fovea, and two of them are the peripheral, coming from the peripheral side of the eye. So, and they are the ones that also go to superior colliculus. How do these cells grow to the right location in the LGN? Okay, you've got a bunch of ganglion cells, and they leave along the optic nerve, and they try to go to get to the. They have to get to the right part of the structure, and the way they do that is by something like a chemical gradient. And a chemical gradient first develops on the socket of the eye, okay? So the sort of along the head. And again, you have the green is the side that sees things out in the temporal side, and the red here sees the medial side. Now, the first thing that happens is that the ganglion cells here adopt the same gradient that the socket had. Okay? And so each ganglion cell has a certain scent it has, chemical gradient, and it's different from the one beside it. And the LGN develops, and it develops a similar gradient. So first, cells from the medial side of the eye start developing, and they're the ones that cross, and they go to specific parts of the LGN that they're looking for. This is a shade of green, this shade of green, so it heads for a part of the LGN with the same shade of green. Then cells in the lateral side of the eye their axons start growing out, and they're the ones that don't cross and that end up in the ipsilateral LGN. And again, they grow to the correct spot in the LGN. Now, what do we not know about the LGN? And there's several surprising things that we don't know about the LGN. First of all, why does it have so many layers? It would seem that at worst 4 would be enough, but for some reason it has 6. The other surprising thing is that most of the signal to the LGN doesn't come from the eye, but from the brain itself, okay, from the primary visual cortex. And as I mentioned in the first lecture, Everything that we perceive is dependent on two things: what's coming in, but also the memories of what you had seen previously, and they're modulating what you see. So they're trying to fool or improve on what you see, depending on what the expectations are. The other surprising thing is that the receptive field of the LGN neurons stay the same. There's that circular surround on and off that we saw. Now, understanding what the LGN does is important because the LGN is just one part of the thalamus, and whatever it does, whatever the LGN does, the rest of the thalamus will do as well. So if you figure out these important questions, it'd be a long way towards figuring out what the thalamus does as a structure. So from the LGN, the signal goes to something called the primary visual cortex. It's located here at the back of the eye. It's this blue thing here. And you can see very little of it when you look from the side of the brain. This is the outside of the brain. But if you take the brain and you divide it into two halves, you can see the medial side here, and a lot of the primary visual cortex surrounding this structure here, which is the calcarine sulcus. Okay, so most of it is seen from the medial side of the brain. Now here what we're doing is we're blowing up the brain. So imagine that the brain was a little paper bag that you had crumpled up. And this program here takes that brain and blows it up from its normal convoluted shape. And so you can see what's inside each of these folds much better. So now you have V1 unfolded. And if we look at it, we can find out what different parts of the visual field again light up. You can see that over here, this is above where we're looking, so a signal will appear below the calcarine. Okay. The other thing you'll note is that this is the peripheral retina, and so what's lighting up here is towards the front, the part of the V1 that's towards the front of the brain. Okay. If, on the other hand, we put a light here, we see the same thing, but now above the calcarine, but again in the front side of the brain. To see something in the back of the brain, what we need is something close to within the fovea. And you can see that this lights up this part here. And so this small region here, which represents the fovea, lights up half of or a quarter of V1. And this does the same thing for above, to the structures above the calcarine. Okay, now what else is interesting about this? Well, here's a sort of slice into the brain. This is the surface of the brain. This is what's inside the brain. And you see here a thin layer of gray. And that's where the cells are. It's called the gray matter. And gray matter is important because where the cells are is where the connections are between the different brain structures. Where the connections are is what allows you to remember things. So it's where your memory lies. A change in connections is a change in your memory. Now, below this gray matter, you have white matter. White matter is all the wiring. So it's all the axons, then sending their signals from a single neuron to many different parts of the brain. Within this gray matter, we've got layers. This is the surface, this is the white matter, and we've got 6 layers. And the deepest layer is called layer 6. The one on the surface is called layer 1. An important one we'll refer to is called layer 4C. And that's thick, you'll notice in the picture here, because it has this massive input from the thalamus and from the eye. Okay. The eye sends a big signal to the cortex, to this region of the cortex. Now, what's happening in these neurons? So, in these neurons, you have cells in layer 4C, and this is a signal coming from the LGN, the thalamus. So it goes from the thalamus to layer 4C, and you can see both have these circular receptive fields, as we saw in the retina itself. And if a spot of light is inside the positive portion of this, then the cell will fire. If it's in the peripheral, the cell will be quiet. Okay, how from that we get to simple cells? So you can see one here. A simple cell is different from a layer 4C cell in that it has a receptive field that's elongated. Okay? In this case, it's elongated in the horizontal direction. That makes it very sensitive to the orientation of lines, and it's most active when the orientation of the line is horizontal, okay? And least active when it's perpendicular to the horizontal. How do these neurons, the other type of cell that you find in primary visual cortex is the complex cell. The complex cell is like the simple cell in that it likes a particular orientation. Okay? This one here likes a horizontal line passing through its receptive field. So that's what's similar to the simple cell. But what's different from the simple cell is that the receptive field is much larger. Okay? So you can see a particular line at a particular orientation over a much larger part of the retina. The other thing that some simple cells have, some complex cells have, is that they're sensitive to motion, moving lines, than they are more to moving lines than. Okay. So, how do you make a simple cell that's sensitive to a horizontal line? Well, here you see the receptive field of LGN neurons, which are similar to the receptive field of ganglion cells. And suppose you pick 3 ganglion cells all along this horizontal direction. These cells here would have a similar configuration as would these. And if you combine all these onto a simple cell, that simple cell will have this shape of receptive field. Okay? It will be a bigger receptive field, and it'll be sensitive to a horizontal line. Now, in the case of complex cells, you have the same process occur. 3 simple cells will combine onto a complex cell, making the receptive field larger. But also these 3 simple cells are all simple cells that like horizontal lines. So the complex cell will also prefer horizontal lines. The other type of cells that you find there is end-stop cells. So end-stop cells like lines of a particular length. This one here likes a line just about the length of its receptive field. You can see it starts firing more when the line gets to that length. It fires less for shorter lines and less for longer lines. Another type of cell that you might find is a cell that fires when a line ends in its receptive field. Okay, and we'll see more of this line in a moment. As you can see, or this type of cell in a moment. So you can see that when the line ends in that receptive field, the cell fires. Now, why is this important? Okay, and clinically relevant. A lot of you want to be heading for medical type of professions, and does this have any relevance to a medical type of profession? Well, it is in the sense that it tells you how the brain works. This is a good hint of describing the processes that occur in the brain for doing all the things that it does. We'll talk a little bit next week about cells that specialize in recognizing faces, particular faces, and you can recognize that face independent of where it is on your retina. Okay, so you don't have to be looking directly at the person. You don't have to be looking with the phobia a little bit to the side or whatnot. So these cells do something similar to what simple and complex cells do. A simple cell is a very particular cell. It's looking for a line of a particular orientation. So you might imagine that in order to make a face cell, you have to learn to recognize a particular feature, a shape of the eyebrows or something like that. And then the other thing that happens, you have complex cells, which look for that simple cell, for that particular orientation, not just in the fovea, but around a much larger receptive field. And so this process of looking at something particular and then generalizing it over a larger area is a process that probably a lot of areas of the brain are involved with. The second thing is that one of the Nobel Prize winners that discovered this was David Hubel, and he was a medical student that went to McGill and came from Windsor. I mention him for one reason, is that he came to teach this class about 20 years ago. So I was invited him to, he was coming to give a big talk at the university. And I asked him if he would mind teaching this particular class. So instead of me talking about all these neurons, he would talk about all these neurons. And he was a very gifted teacher. What he did a lot is have the students do most of the teaching, and he would just encourage their answers in the right way. And one of the things that he discovered is something called a form of blindness called amblyopia, using the study of these cells. And we'll see how that works in a moment. Oh, mouse running. Wonderful. Okay. Remember those end-stop cells? Okay. If there are patients that have a scotoma or a blind spot, a little blind spot that they can't see. I have one just off of my fovea to the right of the fovea, and it's annoying because that's exactly where your eye lands when it makes a little staccato next word, and so I often miss words in the sentence and make mistakes in either typing what I'm typing or reading what I'm reading. It's taken me a while to get used to it. Yeah. Anyways, so that's what amblyopia or these patients have. The other thing they have is if they see a face, like you see here, against stripes that you see here, if the patient looks at the face with this blind spot, of course there's no cells there in the blind spot that can respond to it, and he doesn't see the face. But surprisingly, he sees the stripes. Okay, and more surprisingly, these stripes run right through the place where the face was. Okay, so he's not blind to the face. Doesn't seem to be blind in that area, and yet he's blind to the face. How do you resolve that? Well, the fact that he can see these lines is the property of end-stop cells. Imagine you have an end-stop cell up here, and it would notice that this line ends here, but there'd be nothing over here to indicate that the line ends here. The only place it would end again would be way down here, if he's got a blind spot. Okay, so every time this line appears, even though it's not visible here, it'll fire off a neuron that says a line ends at those 2 points, and you'll fill in that line. Now, you might think this is nice theoretical things, but you'll see in a moment that all of you are doing this at this very right now. So, you have a blind spot. This I should have shifted a little bit more. The fovea is more over here, where the darker spot is, but it's about that size. Over here is where you see all these arteries heading out, and they're heading out out from the eye, and it's also where all these ganglion cells exit through the optic nerve. And because you have a big nerve here, you don't have any neurons that sense light, no receptors, no rods or cones in this area. So all of you have that, and yet you're not blind. You close your eyes, you close one eye, and close the other eye. You don't see any big blind spot, which is huge. It's larger than the moon would be. Okay, so let me show you that where the blind spot is. Okay, you can probably do this experiment better at home where you have more control over your position relative to the screen. But if you look here and you close your left eye, at this distance, this dot disappears to me. Yeah. So if you put your eyes about the same distance and look at the square X, okay, you should not see the dot, this red dot. You can do the same thing with paper. Okay? It disappears. Now you can try the same. Whoops, wrong button. Now you can try the same thing for this line. This has a break in it. And if you look at the same X, you'll see a line with no break in it. Okay? You have to keep looking at the X, and just in your periphery, you'll see this line, and it won't have a break in it. Keep doing the same mistake. And surprisingly, if you look at a face, you won't see the face. Not if you don't look at it, but if you look at the X while a face appears here, the face will disappear. And yet, you'll see the lines running through the face. So this is all these, remember the thalamus was receiving all these more neurons that the brain was sending, then it was receiving from the eye. This is what all this stuff from the brain is doing. Keep hitting the wrong button. Well, if this worked, it should work on your colored sheets. You should see that it does the same thing for a blue dot in a yellow field. It appears that the whole field is yellow. It makes up a color that it sees in the periphery for the blind spot. And then you'll see this funny pattern. And again, you'll see that the funny pattern appears where your blind spot is. So the brain is making up this funny pattern in your eye. And it's doing this right now as you look around the room. Okay? It's filling in, and so you don't notice two big like moons that you can't see anything, just black moons. You know, you'd see one on one side and one on the other side. Okay. Where, from what you remember, location of the optic nerve in the pictures that I showed you, where do you think the location of this blind spot is if you were to point to it, left or right? for the right eye. So it's the left, right, I should say. So here's where you're looking. Here's where your blind spot is. So it's something over here. So it's on the medial side of the eye, where the optic nerve runs out of into the cortex. The other thing that's interesting about the cortex is when you switch from the layer 4 C cells to simple cells, you become sensitive to lines, particular orientation. The advantage of that is that you can become more sensitive to small breaks in lines. If you were to look at this from the back of the room, you get to a point where these two things, these two dots, resemble just one dot. Okay? And yet you'll be able to tell that either this or this has a break in it. So all those neurons combining onto a simple cell make it more sensitive to a line of that orientation, to a break in the line of that orientation. So by combining information from layer 4C cells to simple cells, you get an increase in acuity, you get hyperacuity. And the clinical literature that the optometrist shows you is the letters are clear. And they're clear because of two things. One is the acuity that the eyes provide, but also it's also dependent on the acuity of the visual cortex, how well these layer 4Cs are being combined into cells that recognize a particular orientation. Now, we find that when you get to the visual cortex, you get many more cells than in the visual cortex than you have fibers coming in. So you can look at this cell here, and it's contributing information to several cells. In this case, to a cell that's horizontal, vertical, and oblique. Imagine that in the brain you'd have many smaller angles, even smaller than 5 degrees, and so you'd have many cells here representing the few cells here in LGN. Now, the brain also has this columnar organization. You can't see these squares, but you have, in fact, little building blocks called columns. And you can see here the B1 and the calcarine going through it. And you can see that it's again divided into a part that's more involved in the fovea and another part that's more involved with the periphery. But both are about equal. So the fovea has lots of representation in the cortex. And so you can see that what in a sense it's doing is, this is my brother-in-law reading a paper. I'm looking at his nose. And in the cortex, I have this size nose. So many more cells represent where I'm looking than off in the periphery. The newspaper here is large, newspaper here is small. That's because it's in the periphery. Okay, so we've got these things called columns, and there's a surface that we saw before, but they go into the brain. This is all the gray matters, the layers that we talked about before. Layer 6 down here, layer 1 up here. And this big layer 4C in the middle. Now this is important because this is where the signal from the eyes comes into layer 4C. And again, these layer 4C cells have these circular surround receptive fields. The other thing these cells here are, they tend to be dominated by one eye or the other eye. They're mostly monocular cells. As you go above and below layer 4C, you find simple and complex cells. And these simple and complex cells are also different in that they are where the signal from the two eyes first comes together. So when the signal from the two eyes comes together, you can compare the signal from both eyes. And as a consequence, you can see something called depth or stereo vision. You can tell what object is closer to you than farther from you. It is the reason we have two eyes. So each of the hypercolumns extracts the following features. First of all, it gets depth. So here we have one object, another object to the other eye, and then objects to both eyes. And you can see that when one object light is there, one half of this will be lit up, but a little bit of that will spill over to the opposite side in these higher and lower layers. So you've got cells here that are receiving signal from one eye and from the other. Okay, so they're the binocular cells, the cells that help you see depth. The other thing the columns do is see color. In the middle of each of these, except not through layer 4, we have something called, by anatomists, a very striking name, a blob. Okay, that's what they saw, and that's what they named them. And this is where those double opponent cells that we talked about last time are found. Okay? They're the ones that truly give you a sense of color. And then around this center, these blobs, we have like pinwheels. We have little wedges. And within each wedge, you have these simple cells that have a very similar orientation. And around the next wedge, you have simple cells that have a slightly different orientation. Okay, it's kind of an amazing little structure, these columns. Okay, they can do so much. Stereo, color, and depth. They also illustrate an important principle that like cells like to be near each other. So here we have an example within each pinwheel of cells of similar orientation. And then, so these are like cells being near each other. The same orientation drives it. But we'll find other things drive this principle. Okay, at birth, you don't see so much of this structure. This is up in layer 2, so this is where you'd find your binocular cells and simpler complex. And you find this coloring is either a signal from one eye or the other eye. As an adult, we start developing two sides of this column. This side is dominated by this eye, and this side is dominated by the other eye. So that's where the input comes into, and then this input goes up to these other layers. You can see that within these other layers, higher layers, you have, here is a binocular cell sensitive to the right eye, and here is another binocular cell sensitive to the right eye, but both are also sensitive to the left, and the same thing happens over here. And these ones that are sensitive to both eyes generally end up at the edge of these columns. So this is an edge of the column. This is also the edge of a column, and again you can see binocular cells, and this is the edge of the column on this side, and again you can see binocular cells. Did I skip something? Okay. If at birth one eye is impaired, and this impairment is happening at birth, so it's at what is called a critical period. This critical period lasts for a year or two after birth. So if one eye is impaired, that eye is at a disadvantage. And what's happening in your cortex during this developmental period is there's a war going on for representation in your cortex. So all your ganglion cells are sort of fighting for space in your cortex. And if, in this case, one eye has an advantage, it'll take over that cortex depending on what its advantage is. If it's got a big advantage, then that eye will lose its connections to the cortex. And in adulthood, even if you were to repair the impairment, let's say it was a foggy lens, you would still be blind. Now, that's not the case for when you have an impairment. That impairment appears in an adult. I'm gradually getting cataract in one eye. So that means I'm seeing less well in one eye than the other. But my cortex isn't being taken over by the other cortex, because when they when the cataract gets really troublesome, they pop it out and put in a plastic one, and the day after I could see as clearly as when the problems first began. So, but this is different. This is something that happens to the visual cortex and produces a permanent defect in that eye. Now it's been seen that you need stimuli to produce these changes. So light has to enter the eye, and light has to activate these neurons. So if you lived in a dark, completely dark environment, um, these cells would remain in their native state. They wouldn't. The cortex would remain um, uh, binocular at birth, and the columns would not be taken over by one eye or the other eye. Why does this happen? Well, uh, the basis of plasticity is something called synchronous activity. Synchronous activity means something happens at the same time. So in the case of the cells that are doing these changes, it's a receptor called an NMDA receptor. It's located here. And it blocks the input coming from here. And what you want to happen is that calcium goes through this channel and into the cell. So if you get these two cells to fire together, they'll wire together. Okay? And that again is an important principle, especially for memory. So if you're remembering any of this, it's due to this process. Okay, what happens if that was very quick? Maybe I'll go back and do it again. Okay, you saw the little blue things flash, indicating that these two synapses fired at the same time, and then these two at different times. As a consequence, there was a strong depolarization in this cell. So when there's a strong depolarization, these things open up, and they allow calcium to enter the cell. That calcium then produces a growth factor, and that growth factor again goes out through the channels and NMDA channels that were just opened up, and it goes and makes those bigger. At the same time, these other neurons, their connections become weaker because they weren't firing at the same time. So if cells fire at the same time, the connections strengthen. If cells fire at different times, this gets smaller, and gradually the connections become smaller. You see that happening here. Okay, the green ones are firing together. The red ones are firing at separate times. And you can see gradually the green ones taking over the connections. So here we see a similar thing, but now all the inputs are coming in at the same time. So now neither eye has both eyes have a similar advantage, and so both eyes retain their connections. Now that's important for a variety of reasons, but one of which is to ensure that whatever wiring happens is very accurate. Because, for example, when you're looking at this blue line appears in your periphery, it activates this group of simple cells, but from both eyes. This one has to travel all the way from this eye, this one has to travel all the way from this eye, making all these synapses in the LGN and in the cortex, and finally reaching this nice simple cell. But to get that simple cell to fire for this line in one eye and the other eye, you need this connections to form on this neuron and not some other neuron. So the purpose of amblyopia is not the purpose of this plasticity, I should say, is not to produce amblyopia. So it is the plasticity is a good thing, important thing. It's what allows you to tune up the system. So it's important for wiring up the neurons of this single complex cell. Let's now go to a different problem. Okay, this is children with strabismus. Someone who has strabismus, another word for it is cross-eyed. Okay? One eye looks in one direction, and the other eye looks in a different direction. So the same, imagine that there's a cell here in this little column that's looking at a patch, and it never gets the same signal from both eyes. It's either one eye or the other eye because they're looking in different locations. As a consequence, this guy's binocular cells will disappear because there's nothing, no pressure to create these binocular cells. And so you'll develop monocular cells above and below layer 4C rather than the binocular cells we talked about before. Now, what do these binocular cells do? I'd like you to try to cross your eyes. Look at this, the signal on the screen, or on paper, or on your computer, and just cross them. Cross them until you see 3 squares rather than 2. And concentrate. Keep that middle square there. It's fading and then fading actually. Okay. So now I see it as 3, and when you see it as 3, the middle one will be remarkable. It'll be in 3 dimensions, and as you move your head back and forth, you'll see different parts of this 3-dimensional structure. It's amazing. So like that, each eye sees a different part of the flower. So there's nothing in depth for what you see on the screen. But when you do this crossing of the eyes and combine the image from both eyes onto that 3rd square, you can see one flower in front of other flowers, and you can see the relative angle turn and switch as you turn your head. some people like it easier in this direction. What I did here was I took a picture of one flower and then moved the camera over slightly and took a picture again of the same flower. So like your eyes would, one eye, the other eye. You can also do that for this. If you cross your eyes again and see three, the middle one should do miraculous things like the line coming in and out of the screen. Okay, because each eye sees a slightly different version, and this sort of what each eye would see. So this one eye would see this shape. The other eye would see this shape. Some cells that are looking at this part of the figure would have this disparity, so this difference between the two eyes. And you can see red is over here, blue is over here. Cells over here would have the opposite disparity. And if you were successful in looking at the previous games, you'd find that this one here should appear above, out of the page, and this one here below the page, I believe. Why is that? Okay, so here we got the same thing. You're looking at this point here, okay, and then this red dot moves in front or behind that point there. Below here, you see a picture of what one eye sees, and then what the other eye sees. And then if you imagine you combine them and saw what both eyes sees, so you can see that there is a disparity. What the disparity changes is different from when the ball is farther away than when it's closer. Disparity is the key that tells you what the distance is, what's closer, what's farther. And so what you have is lots of cells, millions, each to different disparity. So let's suppose this is one of them. This is one of those simple cells. And we're trying to figure out what it likes. So here's the disparity for looking here and the ball being farther away. As we move closer, the firing rate doesn't change. As we move closer still, the firing rate goes up. As we move closer still, or farther away, in the other direction now, the firing rate goes up even higher. And then over here, at something even closer, the firing rate goes down. So this cell likes a neuron, likes a dot that is slightly closer to where you're looking, okay? Slightly closer to you. There's other ones, other cells that like objects that are slightly farther, and everything in between. So in summary then, the eye flips the image of the world upside down. It also distorts the image in that it magnifies everything coming from the fovea. Then the signal is combined from the two eyes. The first time it's combined, it's not in LGN, but in the cortex, and not primarily in layer 4C, but in the layers above and below 4C. The cortex is sending out information to other structures about things like edges from those simple cells, and then depth and motion, depth from the binocular cells, and color from those double opponent cells that we talked about in those blobs. Okay, so next week we'll talk about what the rest of the cortex does with this information. And we'll see you then. Thank you.